Yeah, maybe short introduction from my side. I'm Aldis Erglis, and I'm running local BI, ML, and AI in data visualization community. Every day I'm working with automation and machine learning solutions. So I'm very close to this technology, and the closer you are to technology, you understand its limitations. So therefore, it's very interesting to hear real stories. And in machine learning and AI, it's still experimentation drives this process. It means we can't predict what will work and what's not. It means that we need to really collect these stories and collect use cases and then understand and think how we could apply some parts of it or fully to some of our problems. So long way to go, and we will start today with these 9 use cases and interesting stories. Okay, let's then start with our first presentation, which will be online, and we could put it on the screen already. So it's artificial intelligence, the driver of innovation in additive manufacturing. If I understand right, additive, it means that these complementary parts in the manufacturing. But let's see, the Pavels, CTO of Exponential Technologies, will give us the first session. Please welcome Pavels.
Thank you. Okay, I can start. I don't think you see my screen. Now you can see it.
Oh.
All good, I can start. Okay, so yeah, hi. Unfortunately, I couldn't meet with you today in person due to some illness. Yeah, therefore I'm attending online. Thank you, organizers, for letting me do so. So the subject of my presentation today is artificial intelligence as the driver of innovation in additive manufacturing. Our company, Exponential Technologies, has been on the market already for 2 or so years. We are actively engaging with companies in helping them solve their R&D experimental problems by providing AI-based tools that help them optimize different black box optimization problems in SLM. So I myself am CTO of the company, basically responsible for the AI algorithms. My scientific background is in laser materials processing and also software programming. Okay, let's start. So let's start easy. What's an AI so that everyone can at least a bit understand? This is how we see it. Basically, an AI is some automated system which is capable of applying exploitation versus exploration techniques to achieve a solution, not necessarily a perfect solution, at least a satisfactory solution for any given industrial problem. In other words, it's also a very simple rule-based self-adjusting pseudo-random number generator that has these emergent features such as that we as humans can call experience or knowledge or learning, or in other words, also bias. Yeah, in our case, we go very simple. Our system, it simply learns by running different kinds of trial and error experiments, which usually look very random to people. But yeah, by applying these exploitation techniques, this guided random number generator actually is capable of achieving the necessary solutions. So I was previously working in the academic environment, and actually the professors, they don't like such solutions because they to them it seems, well, how can a pseudo-random number generator solve my problems? I want to understand the process. I want to understand why laser, for example, interacts with material in certain ways, why all these nonlinear interactions appears and so on. In our case, the AI solution doesn't care about that. It simply solves the problem by applying these exploration exploitation techniques. Now, yeah, let's talk more about randomness. So I thought these two would be perfect examples to prove to you that random algorithms are actually like these Monte Carlo simulation-based algorithms are perfect solvers for any optimization problem. Like for example, yeah, this is actually a book, A Random Walk Down Wall Street, where like the author explained how simply choosing stocks at random could yield you a portfolio which performs just as good as if you were to like invest in some hedge fund with some experts. And the most recent example related to cryptocurrencies is like if you actually put a hamster, in this case, Mr. Gox, into the cage where the hamster can like select a cryptocurrency and then select the choice whether to buy or sell it. And the hamster can actually either perform as good as an average investor or even better, right? So this is crazy. And the funny thing is these random Monte Carlo simulation-based algorithms can also be applied to more like offline, more fixed industrial optimization problems. So how do we explain these problems to the AI? And this is where human intelligence comes into play, and it's very important. So every optimization problem, it must be in some way scaled down, or in other words, simplified and abstracted. Like all the complexities have to be abstracted so that we come up with some basic black box, which only has some inputs that we can interact with, and it has some outputs that we can measure and optimize. So our task is basically to connect the artificial intelligence, basically some solver, to the inputs so that the AI itself can run different kinds of experiments on the inputs in order to get the appropriate outputs. It's an iterative process. Every iteration, it takes some time and some money. So if the optimization algorithms that you are using are actually good, then you can minimize the amount of resources you need to spend on any black box optimization problem. So yeah. Now let's explore the case study where we actually talk about additive manufacturing and what that is and how it fits into the framework of black box optimization. So when we look at additive manufacturing problems, and this is actually where our company started and has the most experience in, is like let's define the additive manufacturing as a black box problem. So we have on the left side we have inputs. Usually the classic ones for selective laser melting, which is one of the most important current additive manufacturing technologies. Yeah, I will actually explain what that is. So selective laser melting, as you can see on the GIF on the right side, is basically how we control the laser beam. Here it is in green, how we control the mirrors, and how we scan the surface, where surface, so this gray area, it's a powder. And basically we do some kind of microscopic welding. We weld the individual powder particles together by applying laser light. So laser light, it interacts with the material particles and fuses them together because when the powder absorbs the laser light, it heats up, it becomes liquid for some microseconds, and then it immediately solidifies. And by controlling the mirrors, by controlling the scanning speed and the hatching distance using the mirrors, you can actually select where the laser beam is applied for every layer. As you can see, this black part, which is being printed, so we scan every layer, we fill every layer once at a time. It's a relatively slow process, but by the end of the day, we get the solid part. So yeah, the easiest way to define to artificial intelligence the additive manufacturing problem is to define its inputs first. And there usually are three most popular inputs: the laser power, this green beam here, the scanning speed, and the hatching distance. These two are geometric parameters, all controlled by the mirrors. Then on the output, this is what we can measure, but what we cannot directly set on the machine. So for example, we can print this part. It can turn out very good, or it can turn out with very bad quality. And so these properties or qualities, or as we call them, outputs, can be, for example, density of the printed part, where by density we mean how many grams per cubic centimeter there is, or there is also concept of relative density. For example, 100% is the best relative density you can get. If you get 80% relative density, it means that your printed part is very porous. It's filled with air inside. Then there are also other properties like tensile strength, elongation, cracking tendency, and so on. So yeah, now more about our product itself. So we are developing a general product. We call it XT-SAM. It's used for defining and solving any kind of black box problem, be it additive manufacturing, biotechnology, chemical, specialty chemicals, or for example, model hyperparameter tuning, etc. And we also are developing a specialized product called XT-AMI for specifically for additive manufacturing problems, such as selective laser melting, which we just explored in the previous slide. Selective laser sintering. This is very similar to selective laser melting. The main difference is that you are not printing metal powders, you are actually printing like plastic powders, but the process is very similar, although it has some differences because you must also control the inner, like the chamber temperature and atmosphere, in the chamber, etc. Then very popular, the most popular printing technology called fused filament fabrication. This is where all the hobbyists are in. Basically, you have a wire of plastic. This plastic, it can be infused with some other particles to enhance the properties of the final printed parts. But the idea of FFF is that you print this plastic also layer by layer. You move the head of the printer and you fuse together the plastic wire, which is melted for some short period of time, but then it immediately solidifies due to the ambient temperature in the room. Then, of course, the wire arc additive manufacturing. This process is approximately the same as fused filament fabrication. The main difference is that in fused filament fabrication, you are mostly using different kinds of plastics like ABS and PLA, but in wire arc additive manufacturing, you are actually using the metal wires and you apply energy to them, like a certain voltage, current, and the wire also, it gets liquid for a for a split second, and then it solidifies. And your task is to control the robot, which does this automated welding. And then directed energy deposition. This is kind of similar to the selective laser melting, where at the same time you apply both. You shoot from the nozzle some metallic powder at some pressure, and at the same time, you're also applying a laser beam so that this powder, which is flying from the nozzle, gets liquid and then solidifies as it lands in the specified position. Then, now, to explain more how exactly our software works, I have prepared this graphical, like an animation. So we see our software as a navigation system that proposes to you solutions which you have to try in real life. Basically, you have to spend some resources, and then the software it tries to find the optimal solution. For example, in this GIF, the optimal solution is in the top right corner, but as you will now see when this, so it reloads, as you can see, the software doesn't immediately know that the solution is there. So it applies these trial and error techniques, tries to explore the whole search space, in this case defined by X1 and X2. So these are two inputs. It tries different combinations. It looks at what works and what doesn't. And once it understands that, wow, there is actually a high chance of getting good results in this top right corner, you can see it starts to exploit this region more and more, and it doesn't really exploit the resources where like there is a less chance to get actually good results. Okay, so from this, yeah, the demo, not only presentation, we actually also have a software product, which I can show you now. I hope really you can still see my screen. I'm not sure that you can see my screen, unfortunately. Share screen. Yeah, now it will be. I think you can see it. Yes. I will close the slides now. Okay, and now do you see the Google Chrome? Perfect. Thank you very much. Perfect. So this is how our software looks like from the user's perspective. This is the experiment view, which I was talking about. In experiment, we define to the software the inputs, like in this case, as you remember, laser power, scanning speed, and hatch distance. And how we define it to the software, we simply tell the software what is the minimum possible boundary and maximum possible boundary. Now the software knows that for this specific parameter, it can search from 50 to 200. Very similar to scanning speed, very similar to hatching distance. Now the outputs, or as we call them in the software, objectives. Here you can see we have two outputs. One is the density. In the density, we want to achieve a specific density of 8 grams per cubic centimeters. And at the same time, we also want to maximize the tensile strength. So basically that's it. This is how you define the experiment. And yeah, so let's run the quick demo now. So there is the button, you click the generate series, and the software comes up with 10 configurations that you actually have to try in real life. So this is the first, the second, the third, and your task is to enter these numbers into the actual SLM machine, do the prints for each of the 10 configurations, and enter the density value and the tensile strength value. I already did it, so I can simply import the file that I have. Like this. So I will now explain. As you can see, we still have the 10 configurations. Now we see that one of the samples failed. This is why it doesn't have any measurements. The other ones achieved some values for density, some closer to 8, some not so close, some have high tensile strength, some not. Our software sees the samples, it assigns them so-called score. We can sort the samples by score and immediately see which of the samples currently performed the best. For example, this configuration of 147 watts, 420 millimeters a second speed and hatch, it achieved 7.5 grams per cubic centimeter density and 380 tensile strength in megapascals. So now the software can sort the samples. It knows perfectly that this was the worst performing sample, the next worst performing sample, and so on. So now it can come up with a set of next 10 configurations that we can try. So here we are. So now the software proposes to go into this direction in the 3-dimensional search space. So I already did it. I already ran these numbers. I already have the measurements for them. So I can simply import them. Yep, here we are. So now what we have, I will zoom out a bit. Now what we have basically our experiments. Now our SLM experiment currently consists of 2 tables. This is the first experiment. This is the second experiment. So now we actually want to ask the software like, okay, given the data that we currently have, where would the optimal solutions actually be? So what I just did, I asked the software to generate me 100 samples so that we can get an impression and the feel of where the software, quote unquote, wants to go. It takes a bit of time, not too long. Yeah. Should be any second now. Okay, here we are. As you can see, I just generated the series tree. It's a temporary series. It consists of 100 different configurations. We don't have resources to run them all, and we are not going to. We just want to understand where these numbers cluster together. So for this specific purpose, we have developed a like a visualization tool where we can hide the series which have been run on the actual machine, and we can only visualize the the third series with recommendations. And so these are the 100 points which I just generated. Oh, yeah, I will try to zoom in like this. Yeah, so basically here I scatter plot the power parameter and the speed parameter. And what you can see, these 100 scatter points, they cluster together currently in two specific regions. So to an expert, this immediately tells that, okay, I think I should explore or exploit these regions a bit more. So something between 100 and 110 watts. And there is a second potential optimal region like between 140 and 150. So our software, by using these exploration and exploitation techniques, it tries to never stay in some local optima positions. So therefore, as you can see, it always tries to explore some different aspects of the available search space. We can scatter plot this. Yeah, this is very interesting. For example, here we can see that, okay, software once again thinks that it has two potential regions to explore or exploit. This also means that either your optimal solutions are in both regions, or the software maybe or as you progress with your experiments, these hot regions, they converge into smaller and smaller regions, actually just showing you, pointing you with the digital finger, like where the actual solution could be. Oh, sorry, yeah. The last one. Oh, this is cool. So when I do the speed versus catch parameter, here, for example, the software is quite certain that this could be the region we must exploit more and more. Okay, that's all from me. Thank you very much. Any questions?
Okay, thank you, Pavel. So if you have any question, please just raise hand and ask. So question from my side. So as I understood, you are applying more statistical analysis for getting this information. Are you also looking for like something like computer vision and like look at these objects visually and try to detect the same stuff?
Absolutely. I will just stop sharing. Yes, the answer is yes, absolutely. So the vision systems, they, on the one hand, they help us automatically measure the defects in the printed parts, which is perfect. This means that we can connect the visual system directly to our artificial intelligence solver, so that it can feed the data automatically and the experiments can be run in the automatic loop. So currently the experiments still require lots of human interaction. So it is the human that looks in the microscope. It is the human that cross-sects the printed parts to understand their density and other properties. But yeah, vision systems could definitely, so the same techniques that people use in vision systems to understand whether a biological sample has cancer cells in it, the same techniques can be applied to SLM, where the vision system can detect how many cracks and pores are in the printed samples to evaluate the quality. This is one hand. On the other hand, we can also see the visual learner as a black box mechanism, a model that we can also optimize. So for example, a visual system, when you train the visual learner, you try to achieve such input parameters, optimal values for such input parameters as the learning rate. The learning rate as a function, for example, learning rate during the training should change. For example, it should become slower or faster. Then the batch size, the layer structure of the visual learning, for example, how many convolutions there are and so on. So yeah, there are two specific cases how we can apply the visual learners in our case. Yes.
And maybe also a question about this problem in 3D printing. So I'm not a 3D printing expert, but I assume that it's quite stable and precise. So what is actually problem in 3D printing?
Yeah. So the bottleneck problem that we are trying to solve is the parameter development, basically so that the prints are stable as you would wish them. So currently there are issues that you can buy a 3D printing machine that can print metal, but if you don't have the parameters developed for it, then you will struggle to set up your machine. And the setup process can take you, for example, half a year. And during this half a year, you have to pay data scientists, experimentalists, engineers, so that they can come up with these printer parameters, which is a very difficult optimization problem due to the way how the laser light non-linearly interacts with the metal particles in the powder. Our solution simply views the SLM process as a black box. It doesn't necessarily know that it's even dealing with the SLM process. It just understands that, okay, there are 3 inputs that I can play with. There are 2 outputs that give me the reinforcement that I need. For example, whether the previous input led to the good result or it led to the bad result. And yes, so given our experience, we can fasten this optimization process from half a year to just a few weeks, where a few weeks is actually the taking, like the printing and taking the measurements. Our software itself, it can generate the configurations in seconds. Yeah.
Okay. Thank you, Pavel.
Thank you.
If no questions, so thanks very much. And we are going to our next presentation. Dimitris from CEO of SummarizBot. So please welcome. Yeah. Let's encourage him. And Dimitris will talk about content summarization. Yeah, he's picking his microphone. Yeah, some technical break. Yeah, hope to hear something about probably language processing. Actually, language processing is a very promising field of AI ML currently, and I see that many companies and clients trying to use natural language for different kind of analysis, and if previously NLP was like not so popular in data extraction, but more in probably translation and stuff like that, then now language understanding and language processing is almost everywhere. So we try to extract the knowledge from language, extract the entities from documents, and yeah, today also we will hear a couple of use cases where the language processing helps us to build some very useful applications based on AI. Okay.